Hello everyone. In this video, I'm going to show you how to add the SPI device in the PetaLinux platform. And we are going to create the PetaLinux application to control an external SPI LCD panel. We will still use the ZC706 board, and the basic PetaLinux project we already built in the last video. We were going to use that as our base platform. The video link on top of the screen. Now let's start the project. So previously we built the bare metal basic ZC706 project on the PetaLinux platform. The ZC706 already have lots of devices, but there's no SPI in the design. So in this video, we're going to enable the SPI hard IP core in the Zynq core. The hard IP can use either predefined pins or EMIO pins, but because all the predefined hard pin already used by other devices, so we have to use the EMIO pins and link the external to the fabric to go to the FPGA I/O. If you are going to do your own schematic, you can choose to use the hard pin if you don't use the USB or other UART devices in your design. So once we enable this, the icon of the Zynq block will have the SPI pins here. And in the previous design, we used the ASIC GPIO to control the LED, but right now we need to use this to control our LCD panel for the extra pins other than the SPI bus. So we will remove the LED from the design and to use the GPIO and the SPI link to the external pins. On the ZC706, the limited connections you can use, one is the PMOD pins. So I'm going to use this PMOD header, which 4 of the 8 pins will be used as the SPI bus, and the other 4 will use as the reset, data command selection, or backlight to control the LCD panel. So to use those pins, I have to wrap that into a constraint file. So we will add the constraint file to our project. As you can see, it's just a basic pin definition with the I/O standard. And also, we're going to wrap the SPI I/O bus to the FPGA pin, also the GPIO to the FPGA pin. So I already have that in a wrapper file. So all the source files can be found in GitHub. I'll provide the link in the description of this video. As you can see, I just mapped the SPI bus to the PMOD I/O, use the Xilinx I/O buffer, and also the LCD controls for reset, etc. Now we can add this module into our project. we will connect the SPI pins to the wrapper file. You can direct connect the SPI 0 to SPI, but since there's only one device, so I'm not going to use the SS1, SS2 pins. So I will connect all of this individually, and plus later on I'm going to add the chip scope to monitor those pins in case we need to debug anything. We will also connect the GPIO 4-pin bus to the LCD control. And the ASIC GPIO module previously was defined to use the board's LED 4-pin, but right now we are going to connect to the internal fabric, so I'm going to remove that and make sure all 4 are outputs. Now we are going to bring all these pins to external. Use shortcut Control T. Notice that the pin name is automatically generated because there's only one instance, so a 0 is at the end of the name. So very important to match this to our constraint file. Otherwise, you cannot generate the bitstream. Our constraint file is using the schematic NAC name, so there's no 0 at the end. We will also add a chip scope here to just monitor the pins. We will monitor the SPI bus and the 4 LCD control pins. The clock, we're going to use the generic ASIC clock, that's okay. So we'll monitor the clock output, clock tri-state control, and the 4 LED control pins. So hardware-wise, that's all. We can check. Looks good. And we will generate the output file for the IP. Okay. Now the wrapper for our top module should be updated to include those pins which we are going to use to control the external LCD. Now we will generate the bit stream. Okay, now the bitstream is done, and then we will need to export it and bring up the writers. I'm going to create the new folder for the software. Now we will export the hardware include bitstream. And then we will launch the Vitess. Because we are going to create a Linux app to control the SPI. So we have to use the Vitess. First, we will need to create the platform, which is Linux. So the application knows that this will be a Linux application. And we will select the hardware we just exported. The operating system we were going to use Linux. Processor is that one, that's the only one. So everything default should be fine. We will have the first bootloader, the Cortex. Then we just build this hardware. Now we are going to create a new application on that platform. The SPI Linux platform already selected, and then we just name it as text SPI. Everything just leave as default. We just need the empty application. Okay, the structure is here. Now I'm going to bring in the source codes to put in the source file here. Again, all the source codes can be found in my GitHub. So basically, I'm just combine some GPIO demo and some SPI device demo, and plus the LCD manufacturer's demo code for testing the LCD panel. You can briefly take a look at the routines. So I use the GPIO as the main entries and get some parameters argument from the terminal. And then basically this one just to bring the exact GPIO number to the application, because when we build that we don't know what it is. And then once the GPIO is been set up, it will call the SPI device demo. The SPI device demo will then configure itself, enable the SPI device, set the modes, things like that. Once it's done, it will call the LCD initialization. Then the LCD initialization basically will just reset the LCD panel and configure the registers, and then basically we'll just clear the screen with some RGB color, things like that. When the LCD try to pass SPI command or data to the panel, to the port, it will call the GPIO pins to toggle the reset, to toggle the data command bits, and then call the SPI transfer by or transfer strings, things like that, to pass the command or data to the SPI port. So we have all this, and then we build the project. So as you can see, there's a L file created from the whitelist. That's an executable, so we can just bring this to the Linux, and also the hardware platform XSA package. Yeah, so pretty much on the Windows machine here, on the Vivado and whitelist job is done. We're going to move on to the Linux machine. Now we are in the Linux system. I create a folder. As you can see, all we need are 3 files from the Vivado. One is, this is the prop file for the chip scope or the logic analyzer. This is the hardware package, and that's the app we just created in the whitelist. Now, first we need to make the PetaLinux environment. We just create a project. We use the Zynq template, and we can name it as like SPI text. Now extract the get the X. Now this time we are going to boot from the SD card, so pretty much don't need to change anything. All the configurations here should be fine. We just save and exit. That should be good. All the default settings are put from the SD card. Now we need to configure the kernel. The main setting for the kernel is that we need to add the SPI device into the device tree. So after like about 20 minutes, the kernel is ready. And then we need to configure the SPI into the kernel, basically in the device. There's a device driver, and under there should be a SPI support. So by default, as you can see, Xilinx already include the Cadence SPI controller. That's what their hard IP from. The Cadence SPI controller is built in the Zynq core. And then Xilinx also include the SPI controller common mode, SPI Zynq QSPI mode. So what we need to add in to enable is the user mode, SPI device driver support. So we have to add this to support our SPI device. So that's all for the kernel. And then we need to build the root file system. We don't really need to add things there, but for demo purpose, we can also enable the GPIO demo like last time. And if you want, you can also include the BCBox web server, but I don't need that in this demo. So we can just save that. Now we need to build a U-boot. So in 5 minutes, the U-boot is ready. Again, no need to change anything in the U-boot configuration. We just accept all the defaults. So once this is done, as you can see, all the components from the Vivado built-in, it's already put in here. So all the configuration has been put in the device tree. This is the Zynq 7000 default device tree. Basically, there's some CPUs, FPGA, ASIC bus, GPIO, CAN bus, I2C, SPI, UART, etc. So SPI 0 at Z0006 and SPI 1 at Z0007. That's, you can check the Xilinx user manual. Basically, those are specified in there. You can notice that the status is all disabled here. So all the devices basically in this device tree file, it defines the compatibility, clock, interrupts, things like that, but all are disabled. This is all the hardware IP code available in the Zynq 7000. The QSPI is for the boot flash. These are the two SPIs we're talking about. So in this file, everything are disabled but list. And then on top of that, if you have some user IPs adding the logic side, there are additional device trees available here. For example, the ASIC GPIO blocks we add, it's already showing up here. The address as we set up in the address in the block diagram. And because in addition, we enable the SPI 0, so those are all the devices that has been enabled in the Zynq core. For example, the QSPI, the SPI 0 here, we enabled 1. So the status change in this hardware device tree, in the hardware device tree here, from status disable, and then on top of that we enable the SPI device here. Now there's nothing. Also, you notice that the number of chip select has been set to 3. Now there's nothing attached to the SPI 0, so basically PetaLinux don't know anything there. For that reason, if you want to add something on the SPI bus, for example a EEPROM or the flash, that Xilinx has a document showing how to add those tools, but it doesn't show the SPI DUV device that we are going to use here. So for that purpose, I create one of the device tree document like this. Basically, we're going to put this section into the project spec meta user recipes BSP device tree. There's another append device tree as a system user DTSI file. Xilinx recommend you put any your custom device tree in this section. So we put it here. The device we are going to attach to SPI 0 is the SPI DUV at 0, and then we set the chip scope total as 1, and also we set the maximum frequency as 10 because the maximum support on the LCD panel is 10 meg. Then we saved here. Now we just retouch the U-boot. Again, just save and exit. Okay, now we are ready to build the PetaLinux. Okay, so once the build is done, we can package the U-boot image like before. Now it should be ready. So basically all we need are these 3 files, copy to the SD card and then boot from the SD card. We just put an empty SD card there. So it's just empty one. And we copy these 3 files to the SD card. And then we also need the application file. We need to also enable the permission to be executable. Now we also copy this to the SD card. And that's all for our demo. Now we can plug in the SD card. Make sure the board is set to boot from SD 00110. And then we can we can load the putty. It's boot. Now we can check the GPIO numbers. System class GPIO. So as you can see, the higher number is the GPIO we were going to use. The SD card is mounted at the media SD. Here's the SD card. So 3 boot files and the text application we're going to use. So basically we will use that. And then use the G parameter to get the GPIO number here. So as you can see, the screen is flashed and loaded as RGB colors here. Remember, we have the built-in chip scope, so we can also check the pins, how the logic is. So now we will need the chip scope files, the prop file. So we can trigger the chip select pin and see what is the first command come up. So it's just waiting. We can run the command. Now this is the first command. It's 0x36, which is the first configuration command for the LCD. And as you can see, this is the command sent to the LCD SPI bus. So now if you want to see what the continuous data may be, you can just trigger the clock and run this. So as you can see, we are writing FF, FE or something like that, the white bar. Here's the white bar, basically continuously writing on the data bus. Basically, this is how the SPI device is used in the PetaLinux and how to build the Linux application to control the SPI device. Hope you enjoyed the video. See you next time.